A particle of mass m is tied to the end of a light string of length r. The whole system is placed on the surface of a horizontal table. The particle is then given an initial velocity v0 perpendicular to the string. Part 1. If the particle just describes one revolution before it comes to rest, with the string remaining taut, find the values of the initial tension, the friction, and the tangential acceleration in terms of m, r, and v0. Assume that the friction is constant. Part 2. Find also the time taken before the particle stops. Okay, so with these types of questions, it's good to have a diagram drawn so that we can see what forces we're dealing with. Now, we're traveling in a circle, so that means that there needs to be some sort of centripetal force or centripetal acceleration. Now, what kind of motion do we have? We have a particle which is at the end of a string, and that is moving in a circle. So the force that is going to give us this centripetal force is going to be a tension force, which we've got here. I've called it capital T. So the tension force is the acceleration, is the centripetal force in this system, and it's always acting towards the center. That's why we can see it pointing inwards towards the origin, the center of the circle. Okay, so that's the tension force. What else do we have? We have the friction force. Now, the friction force is always going to oppose the direction of motion, and since this is the way that we've defined our motion, going anti-clockwise, so that means the friction force is going to be this way, which would be trying to make the particle go anti-clockwise. So this is our friction force here. So the two blue vectors are the forces in this situation. So those aren't the only forces that we have. We do still have the force of gravity acting on this particle, and that's going to be downwards. So let's say that we are looking at this diagram from a bird's eye view. This is the path that the mass or the particle is tracing, and we're looking from a bird's eye view. So if the gravity is obviously going downwards, this is how we show it. We put an X with a circle around it, and that's mg. And why do we put an X with a circle around it? Well, if you can consider a crossbow or bow and arrow or something, when you're looking from behind, you'll see those crosshairs at the back which make the X, and that's why we draw it like this. And conversely, if we want to show something going up, in this case it's like considering coming out of the page, we draw a circle with a dot inside it, and that's like seeing the tip of an arrow which is just penetrating the page as it's coming through. And what force is this going to be? Well, that's going to be the normal reaction force of the particle from the table. So this is going to be a normal force, call it N. Okay, so now that we have an understanding of what's going on in this system, let's get into the maths of it. Okay, so part I. Now we need to resolve our forces. Well, they're already resolved. We need to consider the vertical case. So vertically, what do we have? Well, we have that the normal force is equal to the gravitational force, okay? And that's all that we really need to do with this. We're not really going to consider this again, but it's good to have it in there for a complete understanding. All right, so that's the vertical. Now we need to consider the horizontal forces now. Now in the horizontal forces, we have two different components. We have the tangential component, and the normal component. So first, let's consider the normal component. So normally, what do we have? Well, we have the tension force, and that's going inwards, so capital T. And what's that equal to? That's equal to mass times the acceleration in the normal direction. So I'm going to call that A sub n. Okay, now A sub n is the normal acceleration, or it's also called the centripetal acceleration because it's inwards towards the center of the circle that we're traveling in. So I can write it as v squared on r, because remember, the centripetal acceleration was given by v squared on r, or also we could write it as omega squared r. But in this case, we're going to write it as v squared r. And that's because we know one other thing, which I'll mention in just a moment. In fact, I'll mention it just now. So what were we told? We were told that we're given an initial velocity v0 perpendicular to the string. Now, clearly the string is our radius because we're traveling in a circle, and we're told that it remains taut, which just means it remains stiff and it doesn't, bend or anything. So if it's remaining taut, then let's say that we're starting, our initial position is on the x-axis. We could define it wherever we want, but it's pretty convenient to define it on the x-axis. So our string is this segment from here to here, from the origin to the edge of our circle. And if the initial velocity given is perpendicular to the string, well, that means it's a tangent, which I've shown in this red vector here. And of course, the tangential thing here means that this is going to be a linear velocity. So v0 is the linear velocity, and that's why we've used linear velocities here instead of angular velocities. So what can I do with that? Well, I want to find the initial tension. So when t equals 0, that will give me my initial tension. What is my velocity? That's going to be v0. And so therefore, let's call the initial tension t sub 0. That's going to be equal to what? M v0 squared divided by r. And in fact, that's all we need for the initial tension. So we have that, that's good. And that completes our analysis of the normal component of motion. Now, let's have a look at the tangential component, which is a bit more involved. So tangentially, what do we have here? All right, let's look at our diagram again. We have the force of friction. Now, friction is constant, so F is just a constant. I've labeled it F, and that's just a constant. So I have the force of friction, but it's going to be negative because it's going in the opposite direction of motion, right? This is our velocity at any point. It's going anti-clockwise, and the friction is trying to make it go clockwise. So we have a negative friction. And that has to be equal to, well, mass times acceleration in the tangential direction. So let's get an expression now for A sub t. So A sub t is minus F on M. Okay, good. Now, recall what was our expression for the tangential acceleration. So, just recalling that the tangential acceleration is equal to r theta double dot. And we've seen that in the derivation video. So that means that I can write this as r theta double dot equal to minus F on M. Now I should say that at this point you can consider continuing the problem in two different ways. You can go off into the angular dimensions or spaces of work, which is what I'm going to do. Or you could in fact continue off in linear space or dimension, and that would also be fine. But the reason I'm doing angular, I'm working with angular quantities is because I think it's good to be able to familiarize yourself with angular quantities, because other questions you're going to have to use angular dimensions or quantities, and since we haven't seen that anyway except for in this section of the mechanics course, we don't see it in 2 unit or 3 unit, I think it's good to do an example like this. Okay, and one more thing I need to do, I need to divide by r, and I get this expression here. Alright, so now I'm going to write my theta double dot, which is my angular acceleration in a particular way. So if you remember back to the earlier parts of mechanics, and even further back to motion in 3 unit, you remember that the acceleration, the linear acceleration, can be written as d dx over half v squared. And there's an analogous way of writing the angular acceleration. It's going to be the derivative of the displacement, in this case the angular displacement. When differentiating, not v, this should be theta dot squared. So this here is like my velocity, it's my angular velocity, and this is my angular displacement. And that's equal to negative F on Rm. And it would be a good exercise, if you haven't seen this before, to try and prove the equivalence of these two statements, because they're equivalent and they often pop up. Alright, so I have that. Now I want to integrate both sides with respect to theta. So, I have this derivative, I'm integrating it with respect to theta, and here I have this term, which remember is just a constant, because F, R, and M are just constants. So I'm integrating that with respect to theta as well. Now, of course, these integral and differential will cancel out, and I'll have a half theta dot squared. And here, well, this is just a constant, so it's negative f on Rm times theta plus some integration constant c. I can move this out of the way now. Okay, so now I need to evaluate what the value of c is. And how can I do that? Well, let's have a look back at our diagram. Now, initially, what did we have? We said that initially we're going to start on the x-axis because that's the way we defined it, and that would make it easy for us. So initially, my theta is equal to 0 because this is the angle theta. I actually haven't written that in or drawn that in, so let me do that. This is my angle theta. So initially, theta is equal to 0. My linear velocity is v0, and that's important, linear velocity. So let's write that down. So far we have that at t equals 0, well, theta is equal to 0. I have that the linear velocity is v0, but I don't have a linear velocity here. I'm working with angular quantities. So let me turn this into its angular counterpart, which would be theta dot is equal to v0 on r, because remember v is equal to omega r, and so therefore omega is v on r. Alright, so I have these now. Now I can substitute these back into this equation here. And what do I get? Well, I'll have a half times v0 on r all squared equals, this term's going to be 0 because theta is 0, so I have 0 plus c. So that means c is equal to v0 squared on 2r squared. And I can write that back in here. I'll have a half theta dot squared equals negative f on Rm theta plus v0 squared on 2r squared. Alright, now remember what we want is the friction and the tangential acceleration. And once I get one of them, I'm going to get the other one because they're related in this manner. I just divide the friction force by negative m and I get the tangential acceleration. So I'm trying to find f now. What other information do I know? Well, let's quickly go back to what the question was saying. It says that the particle just describes one revolution before it comes to rest. That means it starts here, it goes around, and as soon as it gets back to its starting point, that means after a revolution of 2 pi radians, my velocity is 0 because I'm stationary now, I've stopped. So that means when theta is equal to 2 pi, what do I have? I have my velocity, both linear and angular, but we only need angular here, that's going to be equal to 0. So that means I can substitute these into this equation. And this is what I get. 0 equals negative f on Rm times 2 pi plus v0 squared on 2r squared. Rearranging for f, so that's going to be f times 2 pi on Rm is equal to v0 squared on 2r squared. And so f is equal to, let's see, I will divide by 1r on both sides, and I'll have mv0 squared on 4 pi r. And that's my friction force. And so this means that my tangential acceleration, I just have to divide this by negative m, so it's going to be negative v0 squared on 4 pi r. Great, so that's the end of that first part of the question. I have my friction and I have my tangential acceleration. All good there. Now, what about in the next part? It says find also the time taken for before the particle stops. So, I have this expression. I want to write my acceleration in a different way. I want to write it as dv on dt. I could write it as d theta dot on dt, but I don't know why I just chose linear. It's just, I guess, habit. Okay, so if I multiplied everything by dt and then integrated, this is what I have. I have the integral of dv equals the integral of negative v0 squared on 4 pi r dt. Now I could go ahead and integrate right now, and then I'll have a constant. I'll have to work out what that constant is. But I think there's a better way to do it. I think that if we can notice that this is going to be something in terms of t, because this whole thing here is a constant, so this will be this constant times t, and when I integrate this, that will be just v. So when t is equal to 0, what's my velocity? My linear velocity is v0. Now, when t is equal to tf, and that's what I'm just going to call tf as the final time, or the time taken to get to the final point. So TF, when t is equal to TF, what's my velocity? Well, my linear velocity is 0 because I'm stationary. I've come to a stop. So integrating this will be 0 minus v0, which is negative v0. And integrating this will be this constant multiplied by TF minus 0, which will be just the constant multiplied by TF. And now if I rearrange for TF, which is what I want, this is the final time, or the time taken to get to the final point, I can cancel off 1 v0 with 1 v0 here. I can make these positives, and I'll have 4 pi r on v0. And that's the end of the question. We've worked out the time that it takes for the particle to stop.